Hello everyone and welcome to our presentation on WebPerf and evaluation and what is scenario for cloud hosted web application. This work is a result of cutting edge research by Yuang Jiang, Lenin Ravindranath, Suman Nath and Ramesh Govindan in collaboration with the University of Southern California and Microsoft Research. We are excited to share how this innovative tool addresses critical challenges faced by developers in cloud environments. My name is Advait Bharat, and my teammates are Shiva Karthik and Lakshman. And together we will walk you through the motivation, design, and contribution of WebPRF and how it is revolutionized cloud performance optimization. Motivation: developer of cloud-hosted web applications faces significant challenges in predicting how configuration changes impact user perceived latency, such as page load time. These changes, like upgrading a server peer, replicating data across regions, or adjusting workload, directly influence application performance, operational cost, and user satisfaction. Let us consider an example. Imagine managing an e-commerce platform for Microsoft Azure. To improve latency for global users, you must replicate your database to a data center in Asia. While this sounds straightforward, question arises: how would latency change under peak user load? Will the cost of replication outweigh the performance benefit? What if global traffic doubles during a sales event? Without precise tools, predicting these outcomes is nearly impossible, leaving developers to rely on guesswork. Mistakes can lead to slow response time, frustrated users, and lost revenue, or conversely, unnecessary costs from over-provisioning resources. Problem is compounded by the complexity of cloud platforms like AWS and Azure, which offer dozens of service tiers with varying performance and cost characteristics. Developers must navigate these options without clear insight into how changes will affect performance. This underscores the need of a tool like WebPRF to provide systematic, accurate prediction. Why this, why this is an important problem? This issue is critical for three main reasons: impact on users. Latency is a key performance metric for web applications. Research showed that even a 1 second delay in page load time can significantly reduce user satisfaction, engagement, and retention. In competitive market, this often translates to lost usage, reduced revenue, and damage to a brand reputation. Cost consideration: balancing performance and cost in cloud configuration is challenging. Under provisioning can degrade performance, leading to slower response time and frustrated users. On the other hand, over provisioning wasted resources and inflates cost. For example, upgrading a cache tier may improve latency but could double operational expenses if not optimized properly. Cloud complexity: modern web application relies on multi-tier architecture including virtual machine, database, and API, each with dynamic runtime condition and interdependency. Platforms like Azure often define a service tier with distinct configuration and cost, creating an overwhelming number of options for developers to evaluate. These challenges highlight the urgent need of a tool like WebPRF to provide precise systematic guidelines for optimizing both performance and cost. And this is the table to highlight the diversity and complexity of Microsoft Azure Web Server tier, showcasing variation in cost, configuration, and performance. The tier range from standard A0 to standard D14. Performance metrics include response time for a single request, under concurrent request, and at 90% CPU utilization. Higher tier server like D14 demonstrate significantly better performance under heavy workload, with response time dropping from 123,867.6 milliseconds to 552 milliseconds for 100 concurrent requests. This table underscores the difficulty developers face in evaluating cost performance trade-off across configuration. The paper addressed the challenges by proposing WebPRF, a tool to systematically predict latency and optimize server sources without deploying application in all tiers. Existing solution. To understand the need of WebPRF, let's first examine the existing solution and the limitations. Manual testing. Many developers rely on manual testing to evaluate configuration changes. While through this approach is slow, resource intensive, and difficult to scale, For large dynamic systems requiring frequent updates, manual testing often become impractical, causing delay in deployment. Historical data. Using historical performance data can be helpful for application with an established baseline, but it fails to address new deployment or configuration. This method is static, offers limited flexibility to account for changes in architecture, workload, or runtime conditions, which are common in cloud environment. Qualitative SLA. Now, cloud providers often describe performance using vague terms like low latency. This description lacks as quantitative detail developers need to make precise decisions. Without actionable metrics, it's challenging to fine-tune configuration or predict impact of challenges. These limitations reveal a gap in existing methods and highlight the need for a tool like WebPRF. Why WebPRF is needed? Why WebPRF is such a significant advancement? It addresses a critical gap in current solutions by providing accurate prediction. WebPRF often provides insight into how hypothetical configuration will impact application performance. By using dependency graph and latency profile, it can simulate scenarios like upgrading a Redis cat tier or adding database replica, enabling developers to predict outcomes with confidence. Unlike manual testing and automation, which is resource intensive and slow, WebPRF automates the evaluation process, which allows developers to access a wide range of scenarios efficiently without the need of costly and time-consuming physical deployment or each configuration. Cost-effective resource selection. With the abundance of resource options in cloud environments, finding the best combination of cost and performance is daunting. WebPRF simplifies this by simulating trade-offs and helping developers choose configurations that maximize performance while staying within budget constraints. In essence, WebPRF empowers developers to make faster, smarter, and more cost-effective decisions, transforming the way cloud performance is evaluated and optimized. Key insights driving WebPRF. WebPRF reliability and scalability are found in three critical insights. Stable dependency. In cloud application, the sequence of operation by accessing the key value store followed by querying the database remain consistent across configuration. This consistency enables WebPerf to compute castle dependency just once and reuse them for various scenarios. Even in situations involving non-deterministic behavior, such as cache misses leading to database queries, WebPerf accounts for these possibilities and generate accurate prediction for all the possible paths. API modeling. WebPerf focuses on profiling cloud API offline to build robust and latency model. For example, the latency as actual query simply more by the factors like query type and table size by the specific application logic. By identifying these patterns during offline profiling, WebPerf eliminate the need of extensive application-specific profiling, make it highly adaptable and efficient. Let's go to WebPerf architecture. Let's dive into the architecture of WebPerf. It operates through three main components. Input. WebPerf takes three input. The application being evaluated, workload characteristics such as repetitive requests, pattern, and data sizes. Hypothetical what-if scenario like upgrading a resource tier for increasing the user load. Process. WebPRF build cache dependency graph and integrate them with latency profile. These graphs map the sequence and dependency of tasks between the application and output. The output is an accurate latency distribution for various configurations. Developers can use the data to assess the performance impact of changes like tier upgrade or geological modification. In this diagram, illustrate the architecture of WebPRF, showing a systematic process of predicting cloud latency distribution under hypothetical configuration. It have the binary which instrument the application at the bytecode level to capture execution traces, causal dependencies, and runtime data. This instrumented application is executed producing a dependency graph and baseline performance metric to model current behavior. In parallel, WebPR profiler built offline latency models for cloud API, which are stored in the profile dictionary. These models, independent of specific application, account for performance variation based on configuration and workload. The what if engine integrated dependency graph, baseline performance, and API profiles to simulate application performance under the specific scenario. The predictor used probability algorithm to generate a predicted performance distribution which represents how the application will behave under the hypothetical configuration. Next up, the core contribution. WebPerf introduced three key contributions that transform cloud performance evaluation. One is automated instrumentation. WebPerf automate the process of tracking causal dependency within application. This includes handling asynchronous and parallel tasks, which are common in modern cloud environment. By automating this dependency mapping, WebPerf significantly reduced the of uh, manual effort of and complexity traditionally required for such analysis, enabling developers to focus on optimization rather than PDF profiling. WebPerf integrate dependency graph with latency profile to accurate predict the performance of various what-if scenario. For example, it can simulate the effect of increasing user load, upgrading the resource tier, or adding a new database replica. This capability provides developers with actionable insight to make informed decisions before implementing changes. Next is optimized measurement, which profiling every task exhaustively is practical, especially in systems with high complexity. WebPerf address this by allocating profiling resources strategically. It prioritizes tasks with higher variability, ensuring the measurement are both accurate and efficient while minimizing modeling error. This approach delivers precise latency prediction without unnecessary overhead. Together, these contributions make WebPerf a powerful tool for evaluating performance and cost trade-off in a cloud environment. Next up is instrumentation and async application. Modern cloud application relies on heavy asynchronous programming paradigm to improve efficiency and scalability. This paradigm allow operations like database query, API calls, and IO tasks to execute concurrently. While this boosts performance, it introduces significant challenges in tracking task dependency and synchronous point, particularly in high parallel systems. WebPerf addressed this complexity by implementing the application state machine, a core component of asynchronous method. The state machine manages task transition, enabling WebPerf to capture the entire lifecycle of the task, including start when the task is initiated, continuation when dependent operation or trigger or a task resume after an asynchronous call, completion when the task finishes execution. By mapping this task lifecycle, WebPerf constructs a detailed view of the interdependency between asynchronous operations, and this ensures that even in systems with nested tasks or parallel execution, WebPerf can accurately track causality and provide precise latency prediction. This instrumentation is critical for modern cloud environment where asynchronous programming is the cornerstone for efficient system design. Now we are passing on to Sivakartik.
My slide topic is on tracking casualty in task asynchronous application. Uh, we can, in short, we can say TAP for TAP. And TAP is a modern way of writing code that allows tasks like fetching data from a database to run in the background without stopping the rest of the program. It uses simple keywords like async and await to make the code look and behave like normal step-by-step instructions, which makes it much easier to read and understand. For example, in the code snippet, the method process requests run a background task called async task 1. When it gets to await line, it pauses until the result is ready, then picks up the right where it left off. This avoids the messy callback hell that older approaches use. It makes everything cleaner and easier to manage. TAP also helps with running tasks in parallel. This tool allows WebPerf to keep track of what happens when tasks depends on each other or run side by side. The execution flow of tasks to create something called dependency graph. The graph maps out how different tasks are connected, whether they happen in sequence or in parallel, and how they depend on one another. Let's take the example shown here. Two tasks are given. So task 1 and task 2 are initiated at the same time and then synchronized using their task when all and task when any. The flow is seamless as shown in the execution trace figure 6. When the task completes, the program moves to the next step, known as continuation, without blocking other operations. Let's start with the causal dependency graphs. This graph map out the order in which task executes and how they depend on each other, especially in complex applications. They are essential for understanding both parallel and sequential task flows, which help WebPerf predict latencies in cloud system. Now, what's the problem with the existing techniques? Network level proxy limitation. This might be one problem. They rely on timing based guesses, which can result in errors. For example, they might overestimate dependencies, thinking tasks are linked when they are not. They can also misinterpret parallel tasks as sequential. So, another problem is that profiling tool limitation. Tools can be app inside designed for older programming models like APM. They don't support TAPs, unique execution style with async and await. Even modern .NET profiling tools capture only partial dependencies and miss critical async behaviors. Uh, this involves like binary instruments. WebPerf tracks the entire life cycle of asynchronous tasks, including what happens after and await and how tasks are synchronized. It does this by instrumenting the application's binary code. And coming to the execution trace analysis, it uses the traces to create dependency graph, linking tasks based on their causal relationships and synchronization points. Uh, Now let's talk about some challenges. Uh, there are few challenges like implicit callbacks, like tab state machine, often hidden task connection. WebPerf solve this by assigning unique IDs called async IDs to track tasks across their executions. Synchronization points. Tasks often wait for others to finish, like with task.whenAll and task.whenAny. WebPerf intercepts this point to understand how tasks are linked. Uh, and coming to the non-tap calls, not all operations are asynchronous in tap. So by combining this method, WebPerf create detailed execution traces that allows it to track dependencies and predict latencies with high precision, even in complex asynchronous workflows. Uh, WebPerf creates dependency graph to understand how tasks in cloud applications are connected and executed. This graph can be two components like nodes, which represent tasks like API calls or computations, and the other thing is edges, which show relationship like task B can only start after task A finishes. Like casual dependencies or parallel execution of tasks. WebPerf also captures synchronization points like waiting for all tasks to finish when all are just the first when any. To build this graph, WebPerf tracks every operations, identifies how tasks depends on each other, and adds a synchronization details. This process helps WebPerf accurately model how tasks run and interact, making it possible to predict delays. It's like creating a detailed roadmap of task execution to see where traffic might slow things down. WebPerfs help developer evaluate what if scenarios. So it helps by predicting how changes in configuration like upgrading a resource tiers or adding more workload will affect web application latency. It does this in three steps. First, it builds latency profile by testing API performance under different conditions. For example, resource tier or location. And second, it creates dependency graph to map how tasks are connected and identifies their baseline latency. And finally, it combines this information to estimate low total latency. WebPerf uses a profile dictionary to store statistical model of API performance. These profiles are often independent, meaning they don't depend on specific app, but instead of that, it will reflect external factors like service configuration or location. Here are some supporting scenarios by profiling how specific factors impact latency. For example, it can test how geographical location affects API performance by profiling resources deployed in different regions, or how upgrading or downgrading a resource tier can change response times. It also examines how input size and concurrent load impact latency and so on. So WebPerf uses parameterized profiles. This handles cases like SQL queries where latency depends on the query type and table size. Developers can provide workload hints such as table size or cache miss rates to improve predictions. Uh, Coming to this slide, WebPerf is designed with a practical consideration in mind to ensure it remain efficient, scalable, and adaptable. Additionally, WebPerf offer application-specific profiling where it tailors latency prediction to a particular application by combining dependency graphs insight with baseline latencies. This allows for fine-grained scenario-specific predictions and empowering developers to optimize performance and make smarter resources allocation decisions. It's a systematic approach, ensure both accuracy and practicality in real world cloud environment. So coming to the what if engines. In what if engines, in WebPerf, it's a powerful tool that predicts how changes in cloud configuration, workload, or other condition impact the total latency of request. It's designed to simulate hypothetical scenarios and provide developer with actionable insight. Here how it works. So first, as an input, we use profile and APIs. WebPerf relies on pre-built latency profile for various cloud APIs. This profile can be workload independent, which means not tied or specific tasks or parameters. It's just we will be adjusting based on the specific inputs like table size or query complexity. WebPerf uses a dependency graph to map the execution flow of tasks along with baseline. Coming to the what if scenarios as given in the chart, my friend might be explaining about this. For now, it's just an overview that developer can simulate changes such as locations, tier, and input size or inference failure, as shown in the table 2. Oh, coming to the challenges and solutions. There are two key challenges in WebPerf addresses profile selection and enforcing concurrency limits. For profile selection, WebPerf determines whether a task is affected by what if scenarios. If it is affected, it uses parameterized profile with workload hints or fallbacks to workload independent profiles. Otherwise, it uses baseline profile. This approach prevents queuing latency for disrupting performance, ensuring accurate predictions in complex scenarios. And also one more thing, this slide addresses the challenges of probabilistic estimations in latency prediction. Since node latencies are represented uh, as a distribution which is not fixed values, calculating total latency requires complex operations like convolutions and combining distributions. WebPerf solved this by using algorithm one, which is shown in the picture, which is a cloud latency prediction, which recursively computes latency distribution for each node in the dependency graph. This approach ensures accurate prediction for overall request latency by efficient modeling and variability in task execution time. WebPerf combines task latencies based on their execution pattern, sequential or parallel. For sequential execution, the total latency is the sum of individual task latencies calculated using the convolution by combining their distribution. For parallel execution with wait all command, the total latency is determined by the slowest task using the maximum function to combine distribution. This method allows WebPerf to model real-world scenarios accurately, whether tasks are dependent on each other or running simultaneously, ensuring precise latency predictions. WebPerf handles execution with wait any and mixed dependency to model latency. accurately for wait any. The total latency depends on the fastest task, calculating using the maximum latency z, as you can see in the slide, and combining distribution based on probability of at least one task completing within a given time. In mixed dependencies, WebPerf combines both wait all and wait any semantics, where some tasks are must complete all at once, and others only require only one to finish. This is a computed using a combination of maximum and minimum latency operation, leveraging tools like ProbMax and ProbMin to ensure precision. This flexibility allows WebPerf to capture a wide range of task dependencies and execution pattern for accurate latency prediction. Uh, Now my friend Lakshman will be explaining from this point.
So let's now look at the implementation of WebPerf and how it was evaluated through its experimental setup. The WebPerf components, the system is composed of three main components. A binary instrumenter implemented as a NuGet package which automates tracking of execution traces in cloud applications. A profiler which stores latency profiles in Azure table storage for efficient access. And we have the What If engine, a cloud service with a web interface enabling developers to simulate hypothetical configurations and predict their latency impacts. The prediction logic behind WebPerf is written in Python, comprising approximately 20,000 lines of code to deliver accurate and robust predictions. And then moving on to the experimental setup. WebPerf was tested on 6 Azure web applications, with Social Forum serving as a standard example. And Social Forum is a production grade application featuring complex functionalities such as forums, tagging, and search. And this utilizes 5 Azure services, including blob storage, table storage, and Redis cache. And showcasing WebPerf's applicability to real-world scenarios, the complexity of social forums dependencies graph highlights WebPerf scalability. And talking about the WebPerf scalability, it involved 116 asynchronous input-output calls with extensive parallelism. And across all 6 applications, the average dependency graph consisted of 182 nodes, 180 asynchronous await edges, and 62 synchronous points across all 6 applications. And the key highlights of WebPerf is here the scalability. WebPerf demonstrated its ability to handle complex dependency graphs efficiently, even in highly parallel environments. And talking about the real world use case, Social Forum exemplifies how WebPerf accurately predicts latencies for production grade applications, making it a powerful tool for developers navigating intricate cloud configurations. In summarizing this slide, the WebPerf combines advanced instrumentation, profiling, and predictive modeling to provide a reliable and scalable solution for latency estimation. And moving on to the next slide, so let's discuss the scenarios. So now we'll be exploring the 6 critical scenarios developers encounter in cloud-hosted environments, and these scenarios were carefully designed to reflect real-world deployment challenges, helping us understand the latency impacts in a variety of configurations. And to put it simple, we'll break these scenarios into 3 slides, covering 2 per slide. And yeah, let's begin. So here we have 2 scenarios on the slides, so scenario 1 and 2. The first scenario is location change. Here we test with the impact of relocating resources to different geolocations, such as, for example, moving a Redis cache from US West to Asia East. A latency is evaluated using RTT distributions between a front-end and back-end components. WebPerf accurately predicted latency shifts with a median error of less than 4%, enabling informed decisions on optimal resource placement. And then this scenario is crucial for applications serving global users, as developers need to balance latency and cost as well. And then talking about the second scenario, tier upgrade, which assesses performance improvements when upgrading resource tiers. For example, upgrading a Redis cache from standard CO to standard C2 results showed significant latency reduction, and WebPerf's predictions were highly precise with a median error of less than 1%. And this enables developers to weigh performance benefits against additional costs effectively, especially in high traffic applications. And moving on to the next scenarios, and scenario 3, concurrent user load. Here we simulated 10 to 60 concurrent requests for applications like social forum. Even with 30 simultaneous users, WebPerf maintained prediction accuracy within a 10% median error. It's a very good performance number. And this analysis is vital for ensuring scalability in real-world environments where user loads can vary significantly. And moving on to the scenario 4, the input size variations. Examining the latency impact of varying blob storage sizes from 14 KB to 20 MB. WebPerf demonstrated its capability to predict larger input-induced latency increases accurately within a median error under 9%. And such insights are invaluable for applications, especially handling large data files, ensuring that storage configurations align with performance goals. And the next scenario, interference, where CPU and memory stress are introduced to simulate non-isolated cloud environments. For example, we tested latency under CPU utilization levels from 10% to 80%, and predictions closely matched the increased latencies, achieving a median error of under 9%. And this scenario highlights WebPerf's robustness in shared cloud resources, helping developers plan for the worst case performance scenarios. And the scenario 6, failure simulation, where we analyzed the impact of failed front-end server in a replicated environment. In the social forum case, the workload on the remaining server doubled, and the WebPerf accurately predicted the latency increase, maintaining a median error of less than 9%. And this ensures that developers can design fault-tolerant systems with minimal disruption to the end-user experience. And that's with the failures. That's with the scenario 6. And the next, evaluation results. So now let's summarize the evaluation results across all the previous 6 scenarios. WebPerf was tested on 6 Azure applications with a median prediction error of less than 7%. Across configurations, looking at the figure 11, we see three key highlights. The first one is Redis tier upgrades showed significant latency improvements with predictions matching the ground truth. And the second one, front-end tier upgrade maintains similar accuracy. And the third one is request scenarios were handled effectively even with the higher user loads, and these results validated WebPerf's capability in modeling real-world workloads. End-to-end latency prediction. And WebPerf extends its predictions to estimate end-to-end latency, integrating cloud-side latency derived from its predictive algorithms, and we have network latency modeled using RTT distributions, and then we have client-side latency, which leverages browser tools like WebPerf, as shown in figure 12. Predictions remained accurate even for complex setups with median errors under 7%. And next slide is comparative analysis. And let's analyze WebPerf's accuracy across applications and scenarios. And we can say that the simpler applications like Contact Manager exhibited more precise predictions due to the smaller dependency graphs. And whereas the complex applications such as the social forum managed to maintain prediction accuracy despite a 116 asynchronous input-output calls and extensive parallelism. And in scenarios like failure simulation, prediction variability increased slightly due to the workload specific dynamics. And moving on to the next slide, which is about using workload hints. WebPerf benefits greatly from workload hints, which developers can provide to enhance prediction accuracy. For the first point, it's SQL queries on large tables. For SQL queries on large tables, errors dropped from 28.9% to 4.6%, when a query complexity was specified. And in this, and second, in Azure CDN, a caching miss rate hence reduced from 40% to 32%. And these hints allow WebPerf to tailor its predictions to workload specific nuances, ensuring higher reliability. The third one, WebPerf achieves accurate predictions for uniform workloads where there are 1.7% error and significantly improves skewed workload accuracy with hints from 90.1% to 5.9% error. And moving to the next slide, additional results. WebPerf demonstrated robust performance under various conditions. First, it's accurately modeled concurrent limits, achieving a median error of just 2.1% compared to the 87.3% when limits were ignored. And second, prediction errors mainly stem from API latency models ranging from 0.4% to 6.5%, while the algorithm itself has a minimal impact of 0.4% error. And we also have other to extend on additional results. The third one is the optimized profiling process minimized errors while requiring 30% less time than the traditional methods. And fourth is the overhead for instrumentation and predictions remain minimal, making the WebPerf efficient and practical for the real world use case. And that's with the additional results. And then talking about is the paper well organized and presented. And here we are sharing our thoughts about what we thought the paper and how it is. So the paper, the code, the paper is well organized and presented, offering a logical flow of content. It begins with an overview and transitions into methodology covering topics like dependency graph, construction, latency prediction algorithms, and Monte Carlo simulations, and then concludes with the evaluation results. Technical terms such as dependency graphs and probabilistic latency modeling are thoroughly explained, ensuring clarity for readers familiar with the domain. That's a good point. And talking about the figures and algorithms, figures like 8, 9, and 10, along with the pseudocode from the algorithms 1 and 2, provide valuable visual and conceptual support. Concrete examples such as evaluating what-if scenarios like upgrading a Redis tire and further enhance comprehension. In the paper, Key's contribution include introducing WebPerf, a tool for systematic latency prediction, which is also providing generalizable methodologies and bridging the gap between cloud side and end-to-end latency estimation. But overall, it delivers both clarity and practical value to the field. And next slide, what did we learn from this paper? Speaking about what we learned from the paper, this paper offers several key takeaways. It introduces a novel probabilistic approach to latency prediction using dependency graphs, latency profiles, and Monte Carlo simulations, while WebPerf demonstrates its versatility through what-if analysis like tire upgrades and failure modeling. By integrating cloud-side network and client-side latencies, WebPerf provides a unified and actionable view of request performance. Additionally, it achieves efficiency by instrumenting only critical components. And future exploration of this paper could refine network latency modeling, evaluate scalability in real-world cloud environments, and integrate with tools like WebProfit or machine learning for adaptive profiling. And overall, the paper highlights impactful innovations and possibilities for further growth. And they will concluding the paper. The WebPerf achievements, it says it provides accurate, systematic latency predictions for cloud-hosted web applications, and then it saves times and cost by automating evaluation for resource configurations. And future directions include integrating machine learning and expanding API coverage to handle more dynamic scenarios. And thank you for the attention, and thank you for being to the end. And that's our presentation. And we are concluding our presentation here. Thank you. Thank you, guys.